Right, here I am for homework 1 part B. I'll be starting off in the whiteboard again. So we are looking at the CSTR and just deriving the time and, the material and energy balances. So first I'm just going to draw out what we have. We have a CSTR with some flow in and some flow out. Right, this will just be QI, some concentration going in. We'll call it Q naught and CA naught. That'll probably work a little better. It's flipped from what I did from part A, but this way, I don't know, it just makes more sense in my head. It's hard to write I's, I guess. And so now we have 0, 1. This will work later when we do series of tanks. We'll do 0, 1, 2, so on. So we have our stir, and then we also have a cooling jacket, right? Okay. So what we want to do, and this tank reactor, we will just be going from A to B at some reaction rate K. And that K will be derived from our Arrhenius equation, later in Python. But for now, we're just going to say K. And this will be a first order reaction. So equals K, C, A. All right. This should be all of my initial stuff, I believe. So first we are going to look at the concentration, just because it's a little bit easier. So we have the change in concentration times volume over time. The reason why I have volume in here is because concentration is a per volume basis, and we want to look at the total amount of matter, but our volume is constant, so I can just take that out right away. That is too wide. And so this will equal our concentration going in minus our concentration going out. We have Q naught C A naught minus Q1 CA1. Now, this tank is at steady state. Doesn't actually say that in here, but we are going to assume that it's at steady state. So all this liquid on top, it's at its max level. It's not, falling in height at all. And actually everything that runs into here would immediately add to the tank and overflow out the top. So the height at least is at this steady value right at the top of the tank. So that means that our Q naught actually equals our Q1. So we can just take those bits off. And that also means that we can factor out our flow rate here. So we get Q times CA naught minus CA1. All right, and we also have a reaction happening. So that'll be minus K CA times our volume. Because R is, oh wow, that was a bad arrow. R is on that arrow wasn't much better. But R is on a per volume basis, is what I'm trying to get at. Now the next step is just to simply divide by volume, so we can divide by volume here, and take out both of those. So we get our differential equation for the concentration of the tank equals 2 over V times concentration of the stream flowing in minus the concentration of the stream flowing out, which is actually just the concentration in the tank. So this CA1 refers not to the flow going or concentration out, but the concentration of the first tank. And then we can just go ahead and fix this up here. We have KCA1. To make it a little bit less confusing, I'm going to remove these ones and just label this as CA. So this will be our differential equation for concentration. Next, we want to look at the temperature. I'm going to go down a little bit. And so we have our temperature, but we want to look at energy. Right. So we have temperature, which is in Kelvin, multiplied by the heat capacity, which is joules per gram Kelvin. So now we have joules per gram. And if we multiply by our density, we will get joules per meter cubed, and our volume, we get joules. So this is the change in energy over time. Now the reason why I mentioned mentioned temperature specifically is because our heat capacity, our density, and our volume are all constant. Heat capacity does change a little bit with temperature, but for now we are going to assume it is constant. So we can just go ahead and take all of those out. So I'm going to write this a little better. D times rho times V times the temperature D time. Right. So this is going to be from 3 different sources. So first we have this flow coming in, right? That flow going in is at some temperature Ti, T initial, T naught, and this flow going out is the temperature of the tank. So what we can do is Q times our difference in temperatures, and then we'll do a little bit of dimensional analysis here, right? So we have meters cubed per second times Kelvin. So we multiply by heat capacity to get rid of Kelvin. We now have, what is that, joules meters cubed per gram Kelvin? Sorry, gram second. Yeah, well, essentially if we multiply by density, that all cancels out. We end up getting joules per second. So we have, oh, I'm not going to be able to write that well, but I can just do the arrows. So meters cubed per second times Kelvin times our joules per gram Kelvin times meters grams per meter cubed, and that all cancels out to be joules per second, which of course is in line with our dt, right? With the left hand side of the equation. All right, now the second source is from a reaction happening, right? And so that's going to add heat, and we are going to use the negative heat of reaction, which is a positive value because that reaction loses heat. It's exothermic. So it is a negative value, but because that heat is going into the tank, it becomes positive. So this negative heat of reaction is actually a positive value. All right. So now we need our reaction rate, and that is going to be our KCA and it is on a per volume basis because this this rate is at a per volume basis. And lastly, we have heat lost from the cooling jacket. So that is a negative. We're going to multiply by our heat transfer coefficient. That is going to transfer heat based on our temperature difference. So, not T naught. So T minus TC. Now what I'm going to do is divide everything by CP C rho V. So I'll go through. So this becomes over volume, and CP goes away. This becomes over CP, C rho. I keep saying CP, but it is rho, and that gets confusing with heat capacity at constant pressure. And this is over C rho V. And then let me just like clean this up a tiny bit here. Alright. Oh, and I do need to erase these on the left-hand side. So, what we end up having is that our change in temperature with respect to time equals our flow rate times the difference in temperature between the flow going in and the tank, all divided by volume, plus the negative heat of reaction times KCA, which is our reaction rate, over heat capacity times rho, and then we subtract our heat transfer coefficient, UA, multiplied by our difference in temperature between the tank and the cooling jacket, and this one is over C rho V, which is heat capacity, density, and volume. So now I'll be going in, plugging these two into Python, and yeah, so I'll see you there. All right, here I am in Python, and I've already got our libraries imported, and I'm going to do a quick run through here of our initial variables. Sorry, that's variables. Our flow going in is 100 liters per minute. Concentration in is a mole per liter. Temperature in is 350 Kelvin. Our volume of the tank is 100 liters. The density of water is, of course, 1,000 grams per liter. Heat capacity is 0.239 joules per gram Kelvin. Negative heat of reaction is 5 times 10 to the 4th joules per mole. Our activation energy over R is 8,750 Kelvin. Our K naught, which we will use for the Arrhenius equation, is 7.2 times 10 to the 10th, 1 per minute. And our heat transfer coefficient for convection from the cooling water is 5 times 10 to the 4th joules per minute Kelvin, and our cooling water will be at 305 Kelvin. Our initial variables are cooling water at 300 Kelvin, concentration in the tank at 0.5 moles per liter, and temperature in the tank of 350 Kelvin. So now I'm going to go ahead and define our function. So find right hand side for t in a vector, and that vector will be temperature and concentration. then I'm going to go ahead and put in our Arrhenius equation because that is dependent on temperature, so it does need to be in the function. So that'll be K naught times E to the negative ER over T. And then I will type out our expressions for temperature and concentration. So our temperature, we have Q over V times the difference between the input and what is in the tank. And we will add to that the energy gained from the reaction, which is our negative heat of reaction times K times concentration divided by rho times C. And then we will subtract, I'm going to space these out a little more, just so it's a little easier to see. Subtract our convection, so that'll be UA times T minus Tc over rho times V times C. Okay. And then for our concentration, we have Q over V times the difference in concentration minus everything taken out, or everything lost in the reaction. Right, then I can go ahead and set my time, so we'll make it ends at 10. We'll just call this minutes because we are using minutes. And now I can do a result equals solve IVP for right hand side from 0 to time n with a vector T naught, CA naught. Method equals rada U. And sense output equals true. Now we'll go ahead and use sol.res for tplot. So I need to make my time plot. So tplot equals np dot linspace from 0 to time end of 101 steps. And this is actually res.sol. And we will make our variables temp plot and cplot. All right, then non-type object is not callable. Oh, I misspelled thence output. And then we will go ahead and graph this. So figure equals make subplots. And I want 1 row, 2 columns. Fig dot add scatter. X equals tplot, y equals temp plot. Row equals 1, column equals 1, and our name will be temp. I'm going to go ahead and spoilers. Use cplot and column 2. Okay, so now we've got our 2 graphs here. The one on the left is temperature, and the one on the right is concentration. So you can see there are these oscillations, in both, kind of almost mirroring each other vertically. So what ends up happening is when that cooling water increases in temperature, the tank is being cooled less. So the tank then rises in temperature, because if you with these initial values, it's at steady state. All right, so we are now breaking away from steady state, and so we see a rise in temperature. As temperature rises, the heat or the reaction rate also increases. reaction rate increasing means that the concentration falls, but also that temperature increases even faster because the reaction produces heat. Once the concentration gets low enough, there's no more reaction, not enough reaction going on to um, keep the tank at a high temperature, so temperature begins to fall. And the stream coming in, I believe at 350. Yes, so 350. So the stream is also now, um, or I guess the whole time was bringing the temperature down, but the temperature the stream is now bringing in concentration, is bringing in our product or our reactant, and so that's increasing the concentration in the tank. When the concentration in the tank rises, the heat produced from the reaction increases, and then the temperature increases, which increases the reaction rate, and then the concentration level starts to fall because it's reacting so quickly, and it keeps on going through this cycle, just over and over until eventually it might reach steady state, it might not. I haven't really graphed that far. I guess we could see if we go to like 1,000, we'll see if it just keeps on doing this. It'll take a little bit. Overflow. Maybe it'll still work. Oh yeah. So this just looks even crazier. But yeah, it doesn't appear to be steadying out at all. It's just these oscillatory patterns. Yeah. So that'll be all for homework 1, part B. Thank you. Actually, I just thought of something. Um, our T plot is still only 101 steps. So I'm gonna increase that too. This is gonna take a while. Um, if it really does take a while, I'll cut. Oh, no. Oh, let's try some things. I think 1,000 might have been too many. 1,000 was too many. Um, let's decrease that a little. Okay, so now we can get a visible graph. The problem before was just that it was going to 1,000 minutes, but it didn't have very many steps. Now we have, only going to 100 minutes and 1,000 steps, and it's not appearing to have any decrease. Maybe like a degree, yeah, like a degree over 100 minutes. So not really dwindling very much. That'll be all for homework 1B officially. So thank you.